Okay, so welcome to this doubt clearing session of the course Engineering Thermodynamics. Let me take up the first doubt for today. Now all can see my screen. Anyone is there who cannot see my screen? Is there anyone? Sorry?
Sir, it is visible.
Okay. Okay, fine. Okay, so the first doubt is to explaining efficiency equal to 1 at 0 Kelvin, you said that COP is equal to infinity, but with formula it is coming 0 at TL equal to 0 Kelvin. Please explain which is correct. So thanks Asutosh for notifying this mistake. It's actually mistake from my side. So formula for COP of the refrigerator is nothing but equal to TL divided by TH minus TL. So you are correct. When TL will be equal to 0 Kelvin, at that time our COP of the refrigerator will be equal to 0, and we know that COP of the refrigerator is nothing but amount of heat rejected divided by the work input. Okay, so my work input will be QL divided by COP. So COP is 0. So whatever the amount of work which is required to reach a temperature of 0 Kelvin, that will be actually infinite. So somehow I missed this point. So probably I was in hurry. So because of that, I missed this point. Okay.
Yes, sir.
So its COP work required should be infinite and COP will be 0. Okay. Okay. Then next question. How entropy is taken 0 for water at 0 degree Celsius in steam table? Similar to entropy, we have also not found exact value of internal energy. Okay. So let me just tell you this also. So if we see, we will be coming to know from our third law of thermodynamics. If we try to quantify the absolute value of the entropy, we will be finding that corresponding to 0 Kelvin, our absolute entropy is nothing but equal to 0 kilojoule per kg Kelvin. Okay. But this thing will be coming to picture only after understanding of the third law of thermodynamics. At the moment, what I want to say, whenever we are doing the thermodynamic process, we are always interested in change in energy or change in entropy or change in enthalpy. Means whatever the thermodynamic property we are having, we are always interested in finding the change of that particular property between the two thermodynamic states. Okay, so that is how we define our process. So that's why while we specify the property tables, we set any one condition as a reference point for defining the absolute value as 0. Okay, so in case of steam tables, I already explained to you that triple point of water 0.01 degrees Celsius is considered as a point at which our internal energy of the liquid, entropy of the liquid, and specific volume of the not specific volume, it is having certain value, but yes, internal energy of the liquid and this one entropy of the liquid are given as the value of 0. Okay. If you go to refrigeration table, another, so refrigerant is actually, I have already explained you, refrigerant is another working fluid which is used in our refrigeration cycles, refrigeration devices. So in case of refrigerants, you will be finding that for each and every refrigerant, while we are referring to the property tables, we are having some different reference point. Okay. So what we have to do while we are doing our analysis, obviously we have to obtain all the values with reference to a single reference point. Okay. So relative to single reference point, we have to measure each and every property, and moreover, while we are doing the thermodynamic analysis, we are only interested in change of that property. Okay. However, in defining the steam table, we are having some fixed standard reference state, and that is nothing but triple point of water. Okay. Is this point clear?
Thank you, sir.
Okay. Then in the seat, I don't have any other questions. So apart from this, anyone is having any question? Those who are connected?
So can you explain the Clausius inequality? I
Okay.
didn't get.
Okay. So Clausius inequality simply says that cyclic integral of del q by t has to be always less than equal to 0. Okay, so that is a generalized statement, and this particular inequality is applicable for each and every kind of process, whether it's a heat engine, whether it's a refrigerator, whether the process is reversible or the process is irreversible. Okay, so if I take a heat engine which is having temperature TH as source temperature and TL as sink temperature, and say this heat engine is taking QH amount of heat and rejecting QL amount of heat and doing some W amount of work. Okay, so if I consider this heat engine cycle as my system, so for this particular system, if I calculate the cyclic integral del Q by T, that will be nothing but this heat engine is getting QH amount of heat, and this heat is coming at temperature TH. So it will be nothing but QH divided by TH, and QL amount of heat is being rejected. So that's why I have to write over here minus QL divided by TL. Okay. Now we know from our absolute thermodynamic temperature scale, if this cycle is reversible cycle, in that case QH by QL will be nothing but equal to TH divided by TL. So because of that, I can say that QH by TH is equal to QL divided by TL. So as QH by TH equal to QL by TL, so then obviously the cyclic integral del Q by T will be equal to 0. Okay, so that will be applicable when our cycle is reversible. So for reversible cycle, obviously this condition is actually true. Now if our cycle is irreversible, then let me consider now that my cycle is irreversible, and instead of QL, I am rejecting Q dash L amount of heat. Obviously, if my cycle is reversible, I cannot have same heat interactions, because irreversible cycle has less efficiency than the reversible cycle. So because of that, irreversible cycle will produce less work than the reversible cycle. So for irreversible cycle, if I say QH minus QL dash as the corresponding heat interactions, so this has to be less in comparison to QH minus QL. So this will be only true if Q dash L is greater than QL. Okay, this point is clear?
Yes, sir.
So
Got it.
now if I write for irreversible cycle, cyclic integral of del Q by T, that will be nothing but QH by TH plus minus Q dash L divided by TL. Till this point it is correct?
Yes, sir.
Now you see TH and TL are same, and this Q dash L is greater in comparison to QL. Okay.
Yes, sir.
So my Q dash by TL, Q dash L by TL will be greater in comparison to QH by TH. Is this correct?
Yes, sir.
So in that case, it will be nothing but less than 0. Okay. So this I have explained for heat engine. Likewise, you can try for refrigerator also. Okay.
Okay, sir. So in this you have to take the cyclic integral, but today you do not take the cyclic integral. Why?
Today I have not taken. So that is what, like I explained in the morning lecture, that origination of the new property entropy has come from Clausius inequality, which says that cyclic integral del Q by T is equal to 0. But while I have defined today, while I have applied the application of Clausius inequality between two thermodynamic states 1 and 2, first through path A, then through path B, and third through path C, I have found that integral del Q by T from 1 to 2 along path C is becoming equal to integral 1 to 2 del Q by T along path A if all the processes are reversible. Okay. So we have got this particular thing from the Clausius inequality only. So earlier Clausius inequality was applicable for the process, but after doing this application of the Clausius inequality, we have come to know that for a process also we can say that integral del Q by T is nothing but is equal to ds, because it is integral del Q by T is not depending upon the path of the process when we are having the reversible condition. Okay.
Okay, sir. Thank you, sir.
Any other question?
Sir, can you explain again?
Can you repeat your question?
Sir, can you explain again what you said about the COP in the starting?
Okay. So in the starting, I told that I made a mistake in the previous lecture. If you recall, while I was explaining the efficiency of heat engine, which is equal to 1 minus T2 by T1, there I told that when my T2 will be approaching to 0 Kelvin, corresponding to that, efficiency of the heat engine will be nothing but 100%. Okay. So likewise, during the lecture, I told that when our temperature TL will be 0 Kelvin, at that point our COP will be infinite. But that was a wrong statement. So now I explained that this is my COP of the refrigerator. So when my TL is approaching to 0 Kelvin, corresponding to that COP of the refrigerator is nothing but equal to 0. You can clearly see if you substitute 0 Kelvin over here. Now we know the fundamental definition of COP is nothing but heat rejected divided by work input. So now if we see work input equal to QL by 0, so it means work is becoming infinite. It means when my TL is equal to 0 Kelvin, at that time COP of the refrigerator will be 0, whereas the amount of work done required to achieve that 0 Kelvin condition will be infinite. Okay.
Yes, sir.
Okay. Anything else?
So can I ask from the past lectures?
Yes.
Sir, can you please explain about throttling process? I'm a bit confused.
Okay.
Yes, sir.
So say we have situation something like this. Okay. So we have some obstruction over here, and we have over here one say screw with the help of which like we can change our opening, whatever the amount of opening we are having present. Okay. So now what I am doing, one point I am taking on the upstream of the throttling device, and say second point I am taking on the downstream of the throttling device. Okay. So now what will be happening, corresponding to upstream, let me say I have pressure P1, temperature T1, enthalpy H1. Okay. Now we know in case of nozzle and diffuser, when we will be having gradual variation of cross section, during that time our pressure head will be changing. So for example, if initially I have pressure P1, velocity V1, finally I will be getting pressure P2, which will be less than P1, and obviously I'll be getting velocity V2, which will be far higher than the velocity at the inlet. Okay, so that we know when we are having gradual variation of the area. But however, if we are doing sudden obstruction in our path of the flowing fluid, in that case, what will be happening? In that case, I will be having a situation of pressure at the outlet which will be less than inlet. Okay, so pressure will always be less than inlet because we have created some obstruction. So because of this obstruction, obviously the downstream pressure will be less in comparison to the upstream pressure. And we will be finding some temperature T2, we will be finding some enthalpy H2 and some velocity at the outlet as V2. Because we have created the sudden obstruction, so this sudden obstruction though has decreased our pressure, but velocity of the fluid medium will remain almost unaffected because we have not done the variation of the pressure in a gradual manner. Okay, so because of that, I can say that velocity at outlet is nearly equal to nothing but velocity at inlet. Okay, now if I consider that the boundary of this particular throttling device, whatever we are having, that is say insulated. So it means across the boundary we are not having any heat interaction. So Q is equal to 0. At the same point of time, we do not have any mechanical device or any mechanical arrangement made over here which can give some amount of work output. Okay, so because of that, work across this control volume is also equal to 0. Okay, so now if I apply the steady flow energy equation, what will be happening? Let me say M1 dot is the mass flow rate at inlet and M2 dot is the mass flow rate at outlet. Okay, so now if I apply steady flow energy equation, I will be finding QCV minus WCV, this will be in the dot form, plus M1 dot into H1 plus V1 square by 2 minus M2 dot into H2 plus V2 square divided by 2, and this will be equal to 0 because we are saying that our device is undergoing through the steady flow process. So now Q is 0, W is 0. So finally, I will be finding, and also if a process is steady, M1 dot will be equal to M2 dot, which will be equal to M dot. And I have already told you that V1 is nearly equal to V2 only. So I'll be finally finding that my H1 is equal to H2. So it means during the throttling process, what will be happening? Our pressure will be decreasing, but enthalpy of the medium will remain constant. Is this point clear?
Yes, sir.
Okay. Any other question?
Sir, I could not understand the difference between exact and inexact differentials.
Okay. So in case of exact differential, what we are doing, we are writing say dx. So I can simply write dx is equal to x2 minus x1. However, if I talk about inexact differential del x, so I cannot write over here del x as x2 minus x1. It will be actually depending upon the path between 1 and 2. Is this point clear?
Okay, sir. But sir, why it is happening?
Because we have seen that work and heat, though these are nothing but the forms of energy, but these only come into picture while process is happening. So work and heat are not defined at any thermodynamic state of the system. Okay, so at point number 1 and 2, these are not defined, rather these are defined in between the equilibrium states while process is happening. So it means these depends upon the path of the process. So that's why anything which will be depending upon the path of the process and which is not defined at the thermodynamic state of the system, so I cannot write that value as nothing but equal to difference of the magnitude at thermodynamic states. Okay.
Okay, sir, got it.
So, in the throttling process, you have derived H1 is equals to H2.
Yes,
So H is equals to U plus PV, and in lecture you have told that P1 U1 UI plus PI VI is equals to U naught plus P naught V naught.
yes,
And sir, if pressure is decreasing, so specific volume will increase.
yes, correct.
Okay, sir. So, sir, there is any change in the state?
Yes, so because specific volume is increasing, so majority of the time we will be finding that in throttling device, liquid changes to vapor phase. So some of the liquid partially changes to vapor phase. In our subsequent lectures, while we are discussing about the vapor compression refrigeration systems in our applied thermodynamics part, here I'll be telling you about the throttling process in more details. Okay.
Sir, and you have mentioned one more point. You told that for some states pressure decrease and temperature increase, and you have mentioned one term Joule-Thomson coefficient.
Coefficient,
Sir,
yes.
I didn't get it. Oh, actually.
So that is what, like in the initial lecture, I told that we may have the situation where P2 will be always less than P1, okay? But corresponding to this, we may have T2 either greater than T1 or T2 may be equal to T1 or T2 may be less than T1, okay? So which of the condition will be true? That will be controlled by the Joule-Thomson coefficient, and discussion on Joule-Thomson coefficient I will be doing in our subsequent lectures. Okay. While we will be talking about refrigeration cycles in more details.
So when we calculate the work done, which is equal to PdV, basically.
Yes. Yes.
So, but in some questions, we take the work done is equals to 1 by 2 P1 plus P2. That means average of pressure into difference of volume.
Okay. So
There
that is
was
once again, let me tell you, once again, you are confusing. So what we do, you have to understand, we have generalized equation for work as nothing but equal to integral PdV. Okay. So that is the generalized equation for the work. Now, the meaning of this is, say if I have my PV diagram and some process is happening from thermodynamic state 1 to thermodynamic state 2. So my amount of work done during this process will be nothing but integral PdV will be nothing but area under this PV diagram. This point is clear?
yes, sir.
Now, when we are having a system, say piston cylinder arrangement, in which one spring is attached to the piston. So for that kind of system, we have already seen that our pressure volume relation will be, what kind of relation we will be having between pressure and volume?
Yes, sir. You have drawn
Sir,
the
linear.
It will be linear relation. So if this is my thermodynamic state 1, this is my thermodynamic state 2. So what will be area under this?
Okay, sir. Sir, got it. Sir, got it. Thank you, sir.
Okay.
Yes, sir. So actually, it creates confusion many times.
Yeah, so that is only true when our spring is attached to the cylinder. Means relation between pressure and volume is linear.
So can you please explain the use of property table? Actually, there was one question in assignment 4 of CO2 when we use the property table to find the enthalpy. So sir, can you
Okay.
please explain the property table for other fluids also?
So property table for other fluids also looks like same as we have done for steam. So at the moment I don't have any property table available, but like in case of superheated table, we go for we have how many properties are required to find out the property of steam in superheated? Can you tell me?
The 4.
4 properties.
Sir, basically we require 2 property, but there are 4 properties in the superheated table.
Yeah, so 4 are there, but we require only 2 to define the state.
Yes, sir, 2, sorry.
Yeah, so similarly, what will be happening while we are having carbon dioxide? So obviously carbon dioxide is in the gaseous state. Okay. So when it is in the gaseous state, we require two thermodynamic properties to specify its state. Okay. So majority of the time you will be finding when property tables for the gases are given. So we have properties at different temperatures given, and in the top it is written that this table is applicable for say P1 pressure. Then for P2 pressure we will be having some another table applicable. So from that we can determine the value. Apart from that, in case of gases, we are having one more assumption of ideal gas. So when we are considering that our gaseous fluid is following the assumption of ideal gas behavior, under that condition, we will be having only sole dependence of temperature on the properties. So that's why for ideal gas, we will be having a single temperature based property table only. Okay.
Okay, sir. Okay. Sir, and in the practice sheet, there are not answers to the question, so I'm not able to uh, confirm my answer.
So at the moment, I don't have answers available for the practice sheet. So I suggest you people can compare answers uh, among yourselves and then try to find whether these are correct or not. Okay.
Okay, sir. Thank you, sir.
So whether the value of the specific gas constant is given or not in the exam.
If it is for generally it is given. If it is for air, then generally it may happen that you have to remember. Apart from air, normally it is given. Okay, for other things.
Okay, sir. So because in assignment we have a question related to CO2 and we have to find the specific gas constant की value निकालनी.
So in the assignment, we are considering that you all are having access to the books, property tables, everything. Okay. Even I have uploaded detailed property tables. For
Yes,
all.
sir. Yes, sir. So, but I want to know that we have
So generally it is expected from students that they should remember the commonly used values for commonly used fluids. So commonly used fluids are nothing but our air and water. Okay.
Okay, sir.
In competitive exams also it is expected that you should remember the value of Cp and Cv for water and air. Apart from that, it is not expected. Yes, for water we will be having only single value because it's a liquid.
Okay, sir.
Any other question?
Excuse me, sir. Sir, in the
Yes.
transient process, when we consider the energy of system, we take only internal energy. So there is assumption now that kinetic and potential energy is zero.
Yes, yes. So for a closed system, what will be happening? Obviously, we will be having some tank-like arrangement, and that tank-like arrangement, as it is in the stationary position, so obviously we are not having any bulk motion of the medium. Okay.
So, sir, if there is nothing mentioned in the question, so we can take the internal energy of system as its total energy.
Yes, yes, yes.
Sir, in transient process, you mentioned one more point, thermodynamic state should not change. So I don't understand the meaning of it. The thermodynamic state of the flowing liquid doesn't change, or the system that we have
Flowing
take in
liquid,
check.
flowing liquid, flowing liquid.
Okay, sir, okay.
Anything else?